Hello and welcome. So today, we're going to tackle a massive question. What is everything actually made of? For a long time, the simple answer was the atom, this tiny, unbreakable little ball. But as you're about to see, that simple idea was just the opening chapter in a wild story. A story full of shocking experiments, brilliant ideas, and moments that would totally rewrite the rules of physics. So let's jump in and trace that incredible journey. You know, it all boils down to one of the biggest questions we've ever asked. What is all this stuff around us really made of? I mean, if you could just keep breaking down a rock, or a tree, or even yourself into smaller and smaller and smaller pieces, what would you eventually find at the very bottom? This one question has kept scientists busy for over 2,000 years. It's an incredible quest. So, here's our roadmap for this journey. We're going to start way back in ancient Greece and travel all the way to the super weird world of quantum mechanics. And what's so cool about this timeline is that it shows you how science really works. It's not about just finding the right answer on the first try. Nope. It's a story of building an idea, testing it, finding out where it's wrong, and then building a better one on top of it. All right, so our story doesn't start in a fancy lab. It actually begins in the mind of a philosopher with an idea that was way ahead of its time. But to turn that philosophical guess into actual science, well, that would take another 2,000 years and the careful, methodical work of a schoolteacher. Now, this is a really important difference. You've got Democritus back in ancient Greece, and he's basically just thinking, hey, what if everything is made of tiny, indivisible bits? He called them atomos. It was a cool idea, but it was just that, an idea. There were no experiments. Then, flash forward 2 millennia, and John Dalton comes along. His theory wasn't just a guess, it was based on cold, hard experimental evidence. He saw that in chemical reactions, stuff just gets rearranged. To explain that, you had to have some kind of tiny, indestructible particle. You needed the atom. And for almost 100 years, that was the picture. Simple, right? The atom was just a tiny, solid, unbreakable ball. The absolute smallest building block of everything. It's a clean, powerful idea. But, as we're about to find out, science was getting ready to take that simple picture and smash it into a million pieces. So, the late 1800s roll around, and boom, a shocking discovery. It turns out the atom, this supposedly indivisible thing, was actually made of even smaller pieces. This changed everything. Suddenly, that simple solid sphere model just started to crumble. In 1897, a scientist named J.J. Thomson discovers this tiny, negatively charged particle, the electron. And this was a huge problem. Think about it. If atoms are neutral overall, but they have these negative bits inside them, where's all that positive charge to balance it out? Now, a few years earlier, another scientist, Goldstein, had found evidence of positive particles, which we now call protons. So the atom definitely had parts. The big question was, how were they all arranged? So J.J. Thomson took the first shot at a new model. It's famously called the Plum Pudding Model. The best way to picture it is like a blueberry muffin. Imagine the muffin, the cake part, is this big blob of positive charge, and then you have the little negative electrons, the blueberries, just scattered around inside it. It was a pretty clever way to try and explain how you could have both positive and negative charges in one neutral atom. But this model, well, it was about to face a serious test. Okay, now we get to one of the most famous and important experiments in the history of science. Ernest Rutherford, who was actually one of Thomson's former students, decided he was going to test this plum pudding idea. And what he found didn't just challenge the model, it completely destroyed it. The experiment itself was pretty straightforward. Rutherford's team basically shot a beam of tiny positive particles, they're called alpha particles, at a ridiculously thin sheet of gold foil. And then, all around the foil, they had a screen that would light up whenever a particle hit it, so they could see where they went. Now, according to the plum pudding model, these particles should have just blasted right through, maybe getting nudged just a tiny dip. And yeah, most of them did go straight through, but some of them got deflected at an angle. And then, this was the absolutely astonishing part. A tiny fraction, about 1 in 20,000, bounced almost straight back. Rutherford later said it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. It was just impossible. The plum pudding model could not explain this. So, Rutherford had to dream up a completely new model. He realized the only way this could happen is if the atom is actually mostly empty space. That's why most particles flew right through. But somewhere in the center, there must be a tiny, super dense, positively charged core. He called it the nucleus. And when a positive alpha particle got too close, it was repelled. And if it hit dead on, it bounced straight back. The electrons? They must be orbiting way out, far from the center. But as amazing as Rutherford's model was, it had a couple of huge, fatal flaws. First, according to the physics of the time, an electron orbiting like that should be giving off energy, slowing down, and spiraling into the nucleus in less than a second. Basically, every atom in the universe should instantly collapse. But they don't. The other problem was that it couldn't explain why atoms only give off very specific colors of light, what's called a line spectrum. So we needed another revolution. And the solution came from a brilliant Danish physicist named Niels Bohr. He did something absolutely revolutionary. He took Rutherford's nuclear model and mashed it together with a brand new, super weird area of physics called quantum theory. Bohr basically just invented a new set of rules for the atom. He said, okay, first, electrons can only exist in certain fixed orbits, or energy shells, almost like planets on fixed tracks. And here's the genius part. As long as an electron stays in one of those special orbits, it's stable. It doesn't radiate energy and spiral to its death. That solved the collapse problem. And, he said, energy is only given off when an electron jumps from a high-energy orbit down to a lower one. Since the gaps between the orbits are fixed, the energy that's released is also a fixed amount, which corresponds to a specific color of light. And that solved the line spectrum problem. Just brilliant. Now, Bohr's model was a massive success, but with a major catch. It worked perfectly for hydrogen, which only has one electron, but for any atom with more than one electron, the math just fell apart. It also couldn't explain some of the finer details, like why spectral lines sometimes split when you put them in a magnetic field. So his planetary model was a huge step forward, but it wasn't the final answer. The true picture was even stranger. So, to get to our modern picture of the atom, physics had to get weird, like really, really weird. We had to completely abandon the idea of electrons being little planets in neat, predictable orbits, and instead embrace a world governed by waves and pure probability. So in 1924, a guy named Louis de Broglie asked this wild question. We know light can act like a wave in a particle, so could an electron act like a wave? And his theory of particle-wave duality said, yes, it can. This one idea completely shatters the image of an electron as a tiny little ball zipping around a nucleus. A wave, after all, isn't in just one spot. It's spread out. And that wave idea leads us right to Heisenberg's uncertainty principle. Now, this is a fundamental rule of the universe. It basically says that you can know exactly where an electron is, or you can know exactly how fast it's going, but you can never, ever know both of those things at the same time. And this is the final nail in the coffin for Bohr's neat little orbits. I mean, if you can't know where an electron is and where it's going, how can you possibly map out its path? You can't. So science had to throw out the word orbit and replace it with a new word, orbital. And they are not the same thing. An orbital isn't a path. It's a three-dimensional region of space around the nucleus. You can think of it like a probability cloud. It's an area where the electron is most likely to be found. We can no longer say where the electron is. We can only say where it probably is. So how in the world do scientists talk about these probability clouds? Well, they use a set of 4 quantum numbers, which basically act like an electron's address. For what we're talking about today, the 2 most important ones are the principal number, n, which tells you the main energy level. Think of it as how big the cloud is and how far from the nucleus. And the second one, the azimuthal number, L, tells you the actual shape of that cloud. Some are simple spheres, but others are shaped like dumbbells or even more complex things. So let's just take a second and recap this whole incredible story. We started with Dalton's simple, indivisible solid sphere. Then Thomson came along and stuck electrons in it to make us plum pudding. Rutherford's gold foil experiment gave us the tiny nucleus, like a mini solar system. Then Bohr quantized that solar system, putting the electrons on fixed energy tracks. And finally, using the ideas of de Broglie and Heisenberg, Erwin Schrödinger's math gave us the modern picture, the quantum model, where electrons are just fuzzy clouds of probability called orbitals. And this whole journey is just a perfect example of how science works, right? Each model was a step up, explaining more than the one before it, until new evidence came along and forced another big leap. Our picture of the atom today is incredibly powerful and explains so much. But if the history of science has taught us anything, it's that there are always more questions to ask and deeper secrets to uncover. So you have to wonder, what is the atom still hiding from us?